Right now, you believe you know what time is. It moves forward. It ticks evenly. It treats everyone the same. But if you were moving fast enough, or standing near something massive enough, time itself would change. Not your watch. Not your perception. Time. Albert Einstein proved that over 100 years ago. And once you truly understand why, you will never look at a clock the same way again. For most of human history, time was simple. Isaac Newton believed time was absolute. He wrote that time flows uniformly, without relation to anything external. In Newton's universe, there was one giant cosmic clock. The entire universe ticked together. If something happened on Earth, and something happened on Mars, there was a single, shared now. It felt obvious. And it worked beautifully for centuries. Until light ruined everything. In the late 1800s, physicists discovered something disturbing. No matter how you move, no matter how fast you chase it, light always moves at the same speed in a vacuum. 299,792 kilometers per second. This was confirmed by the Michelson-Morley experiment in 1887. And it made no sense. Because in everyday life, speeds add. If you throw a ball forward inside a moving train, someone outside sees it moving faster. So if you shine a flashlight while moving, the light should move faster. But it doesn't. Everyone measures the same speed. Always. This is not theory. This is measured reality. And that one fact breaks Newton's universe. In 1905, a 26-year-old patent clerk named Albert Einstein made a bold choice. He decided to believe the experiments. Instead of questioning the speed of light, he questioned time itself. He proposed two principles. First, the laws of physics are the same for all observers moving at constant speeds. Second, the speed of light in a vacuum is the same for all observers, no matter how they move. If both are true, then space and time cannot be fixed. Something has to give. What gives is time. Imagine a simple clock. Not a ticking mechanical clock, but a beam of light bouncing between two mirrors. Each bounce marks one tick. Now imagine that clock sitting still in a spaceship. The light travels straight up and down. Simple. Now imagine the spaceship moving sideways very fast. To an outside observer, the light no longer moves straight up and down. It moves diagonally. It travels a longer path. But here's the key. The speed of light cannot change. If the light travels a longer distance at the same speed, each tick must take longer, which means the moving clock runs slower. Not because it's broken, but because time itself slows down. This is called time dilation. And it is not optional. It is the only way the universe keeps the speed of light constant. You might think this is theoretical. It isn't. In 1971, physicists flew atomic clocks on airplanes around the Earth. When compared to clocks that stayed on the ground, they were different. Exactly as Einstein predicted. Atomic clocks on GPS satellites tick at different rates than clocks on Earth. Engineers must correct for both. A special relativity, because satellites move fast. A general relativity, because gravity is weaker in orbit. Without these corrections, your GPS would drift by kilometers per day. Relativity is not abstract. It is built into your phone. Now imagine two twins. One stays on Earth. The other travels in a spaceship close to the speed of light. They return. The traveling twin is younger. Not by illusion. Not by biological difference. But because less time physically passed for them. Their heart beat fewer times. Their cells aged less. Their clock ticked slower. Time is not universal. It depends on motion. Einstein wasn't finished. In 1915, he introduced general relativity. Gravity is not a force pulling objects. It is the bending of spacetime itself. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. And here's the consequence. The stronger the gravity, the slower time passes. Clocks closer to Earth tick slightly slower than clocks at higher altitude. This has been measured with extreme precision. Near a black hole, time slows dramatically. From a distance, an object falling toward a black hole appears to freeze at the edge. Time stretches. Gravity is geometry, and time is woven into that geometry. Here is where it gets uncomfortable. If time depends on motion and gravity, then there is no universal present moment. Two observers moving relative to each other will disagree about what events are happening now. This is called the relativity of simultaneity. Events that appear simultaneous to one observer are not simultaneous to another. The idea of a single shared cosmic present does not exist. The universe does not tick together. You don't feel this, because you are not moving near light speed. You are not standing near a black hole. Relativistic effects are tiny at everyday speeds, but tiny is not zero, and reality does not care whether we notice it.